Good afternoon. Today we're going to do chapter 3, which is the special purpose diode. Now, the special purpose diode, it is a Zener diode. A special purpose diode is a Zener diode. Now, with the Zener diode, then we're going to say, what is the symbol of the Zener diode? Now, you'll see that the symbol of the Zener diode, it is the same as the diode, but you will see that it is characterized in this manner. The same as the diode, but it is characterized in this manner. Now, which means once you see on an electrical circuit this type of a symbol, just know that that is your Zener diode. Now, you will see that the characteristics of this component, or the characteristics of this device, works the same way as a normal diode. Works the same way as a normal diode. Now you will see that with the normal diode, you will have the P and the N junction, whereby it is separated by a depletion region. Now, with the Zener diode, then we're going to say on this symbol, we have the anode here, and we have the cathode there. We have the anode here, and we have the cathode there. Now, for this diode to operate, it must be able to operate when it is on a reverse bias mode. It operates when it is on a reverse bias mode. Now, you will see that the characteristics of this component, it is the characteristics of this component according to a characteristic curve. Now, you will see that with this component, you will have the magnitude of the current and you will have the magnitude of the voltage. You will have the magnitude of the current, you will have the magnitude of the voltage. Now, when this component, it is connected on an electrical circuit. Now, you will see that during forward bias mode, this component will act as a normal diode. Now, with the normal diode, you will see that according to the symbol or according to the model, which is your practical model, as we've already discussed this in chapter 2, you will see that you will have an internal resistance and you will have the barrier potential. You will have an internal resistance, you will have a barrier potential, which means based on the material which is used, the voltage drop during forward bias, you will see that it's going to be 0.7 volts. That is during forward bias. Now, the characteristics of these, based on the input, you will see that the characteristic curve of this component will exist in that manner, whereby where the knee is or where it caps, that is where it starts operating 0.7 volts. Now, that is when you look at the characteristics of a normal diode. Now, during forward bias mode, Now, during reverse bias mode on a normal diode, you will see that your existence of the working of this component, the voltage within this component here, it is going to be a voltage whereby this voltage, it is on a reverse bias mode, which means it is of a open switch. We don't or we neglect this part here because there is no current which is allowed to flow within this component. But now, within this component here, it operates when it is on a reverse bias mode, which means when on a normal bias, also on a normal diode, during reverse bias, that is when your Zener diode starts to operate. But now it operates with respect to what we call a breakdown mode. with this breakdown mode, it becomes what we call a knee voltage. With the knee voltage, that is the voltage that is established. That is the voltage that is established within this component during a reverse bias mode. Now, all of these exist within this magnitude here. All of these exist within this magnitude here. Now, when you look at the application of this component here, you will look at this application of this component as a regulator. As a regulator. Now, as a regulator simply means that you will have to have a stable output voltage. You will have to have a stable output voltage. Now, with that stable output voltage, it depends on which type of Zener diode are you using. On which type of Zener diode are you using? Now, if you go to your textbook, there is a data sheet in chapter 3. There is a data sheet of which that data sheet, it is a data sheet that gives the characteristics or the electrical characteristics of a Zener diode. Now, let's see how these components respond with respect to an electrical circuit. Now, when you have an electrical circuit, that will consist of the input, which is your energizer, that will energize the flow of current. Then you will have a resistor, which is your limiter or your diode limiter, resistor, your R limiter. Then you will have the connection of a Zener diode. Now, with the connection of a Zener diode, it is very important how this component is connected. If I connect this component within this magnitude here, if I connect this component within this magnitude here, you will see that this component connected in this manner, with this component connected in this manner, that is your positive side, that is your negative side, which is your anode, and that is your cathode, which means if I measure the output here, I am going to measure the output of a diode, which means how it is connected. It is connected as a normal operating diode. Depending on what is the material used, then you will see that it's either you get a 0.7 volt or you get a 0.3 volt. That is how when it is connected in that manner. But now in this manner, in terms of a diode, in terms of a Zener diode, it is taken as this is in a forward bias mode. That is on a forward bias mode. But now with the Zener diode on an electrical circuit, it needs to be connected. It needs to be connected in this manner so that it can regulate according to what you are looking for. Then you will see that the negative must be connected to the positive, and the positive must be connected to the negative, which means it is connected in that manner there. Now, for it to regulate, for it to give you a stable output voltage, it must be connected in reverse bias mode. Now, in this manner, that is where it is in reverse bias mode. Then the negative there, then the positive there. Now, when it is connected in that manner, then you will get the characteristics working of a Zener diode. But now, to which voltage do we want to regulate our output? To which voltage do we want to regulate our output? Now you will see that for you to be able to know which voltage do you want to work with at the output, then we go and look at the parameter that exists within the characteristics of a data sheet of a Zener diode. I'm not quite sure on your textbook which page it is where you will find, because you are using, I think you are using the 9th edition, but now if you're using the 10th edition, you will see that you'll find it at page 126. The data sheet, you'll find it at page 126. Now, these are the parameters that one needs to work with in an electrical circuit when you work with a Zener diode. Then I will go and say, I will connect an output. I will connect an output load or load resistor, whereby I will be able to measure my output, whereby I will be able to measure my output. Now, with these circuits, it's either we regulate variable input, we regulate variable output, or we regulate your R limiter. Now, with the regulation, simply means that I need something that is of stable. I need something that is of a stable. Now, in this manner, then I will go and say, firstly, let me check if I want to regulate an input. If I want to regulate an input, which means I will want to find out what is the variable input that I can set within my electrical circuit, so that when I measure on the output, I am going to measure a stable output voltage. I'm going to measure a stable output voltage. Then I will go and say, within my electrical circuit, let's say, for example, I give this load as 470 ohm resistor, 470 ohm resistor, and I give this as, for example, 1 kilo ohm resistor. That is the voltage that I am measuring on there. So that is the load resistor that I'm using to measure my output response of this circuit. Then I will go and say, I will have the current which is flowing from my energizer, but the magnitude of the current, I cannot define it at this point of time, because I need to vary this voltage so that the variation of this voltage will give me the stable output voltage, will give me the stable output voltage. Now, if I go and check, I need to go and check within my data sheet. Then I will say the diode that I'm using, I am using a diode of a magnitude of, let's say, for example, you are using 1N, let me just write 1N474, 1N474 2A. Now, this is the diode that I got. So this is the Zener diode that I got from my data sheet. Now, within the data sheet, then I need to find the following parameters. Now, the parameters that I need to look at, it is the parameter of your I Zener minimum, which is your I Zener knee. That is the minimum voltage that the Zener diode can start operating with. That is the minimum Zener current that the Zener can start operating with. Now, if you go to your data sheet, you will see that on your data sheet, under the electrical characteristics, under the heading electrical characteristics, you have got the device, or that explains to you what is the Zener that you are using. It is under the device, and then you have got the Zener diode at a certain Zener current. The Zener diode at a certain Zener current. You have got the minimum Zener voltage, you have got the maximum Zener voltage, and you have got the typical Zener voltage. You have got those three parameters. Now, the parameter that you must look at, it is the typical Zener voltage. Now, with the typical Zener voltage of these characteristics that I wrote on the board, which is your 1N4742A, the typical Zener diode here, it says it is 12 volts, which means the output voltage that I can find, it must be of a 12 volt, which means when I vary this input, I will vary this input so that I can be able to produce an output of 12 volts. Now, that is your first parameter, which means that is your VZ, which is 12 volts. Now, once you get the V, which is 12 volts, which is your typical V 12 volts, then you go and check what is your Zener test current. What is your Zener test current? Now you will see that within the parameter here, within the parameter here, your Zener test current, it is of 21 milliohms. Yes, 21 milliohms. Then I will go and say my IZT, it is 21 milliamps. So ohms, 21 milliamps. 21 milliamps. Now, when I move with these parameters, then I will go and say, what is my Zener knee current? What is my Zener knee current? The Zener knee current, you see that it's represented by IZK. In this case, your IZK is given as 0.25 milliamps, which means it's going to be 0.25 milliamps. 0.25 milliamps. Then you go and check again, what is your Zener impedance? What is your Zener impedance? Your ZZ. What is your Zener impedance? Your Zener impedance in this parameter, it is going to be, your Zener impedance is going to be 9 ohms. Your Zener impedance is going to be 9 ohms. Then I will say my Zener impedance, it is 9 ohms. Now, those parameters are the parameters that you get from the data sheet of the specific Zener that you're going to use. Because according to your electrical circuit, you said you want an output voltage that is regulated, that is being stabilized to be 12 volts, which means if I want my stabilized output voltage to be 12 volts, these are the parameters that I need to look at according to my analysis. Then I will go and say, for me to do the mathematical analysis of these, then at minimum, what is it that becomes important? At minimum, what is it that becomes important? You will see that you will have to go and check. I need the following parameters to exist. I need the following parameters to exist. Then I will go and say, I need to find out what is my V out. What is my V out? Now, in this case, your V out, it is the V out which is given by the V of the Zener minus change of V of Zener. The V of the Zener minus change in the V of Zener. Now, with this V out, what is your Zener voltage? You will see that your Zener voltage, it is given as 12 volt. Your Zener voltage, it is given as 12 volt. Minus, now your change in Zener, it is at which point? Your change in Zener, it is at which point? It is at a minimum point. At a minimum point, which is means it is at a knee current. Knee current based on what? It based on your test point. Then you will go and say my change in Z or of Zener. It is your change in Zener, whereby it is going to be your I of ZT minus your I of ZK multiplied by your I of ZT minus your I of ZK multiplied by your ZZ, whereby it's going to be 12 minus, what is your ZT? Your ZT in this case is what? It's 21 milliamps minus your 0.25 milliamps multiplied by 9. Let's use the calculator and see what will be the result. Okay. It's gonna be 21 milliamps (0.25) then in this case, you will see that your V out here is going to be 9. Sorry, not 9. What did I do? Sorry. 21 to the 3 minus. Which is 11,813 volts. 11,813 volts. Now, with this 11,831 volts, then I will go and say, what is going to be the following? What is going to be the following? Which means now I will go and say, at minimum, then my V in, at minimum, then my V in will be given by, at minimum, my V in will be given by. Then I will go and say, your output, which is the V out, your input will be the V Z plus your V out. V Z plus your V out. Are you saying something?
Yes, may I please ask a question?
Yes.
For the V out there where it's 12 minus 21 minus 0.25 times 9, my calculator is giving me a negative answer and it's not even 11,813.
Your calculation is giving you?
A negative number.
It's 21 milliamps, right?
Yes.
Minus 0.25 milliamps, right?
Yes.
Multiply by 9, right?
Multiply by 9 is 1.
Electronics.
Multiply by 9.
Yes.
Of which that will give you 0.18675.
Oh, okay.
Is it correct?
Yes, sir. I see my mistake now. Thank you.
Then you say 12 minus that gives you 11,18, right?
It's correct, sir.
Is it correct?
Yes.
Okay. Sorry. Okay. Now that is your 11,813, which means your Zener diode, now with this V out or with this voltage, which means your Zener diode will start regulating at a minimum of 11,813. Will start regulating at 11,813. Now, depending on what is your minimum input voltage there. Now, then we're going to say, for us to find what is the minimum voltage so that your Zener diode will start regulating at 11,813. Then we're going to say, my V in, which is your input voltage, it is going to be your V of R. I just made a mistake before. Your V of R plus your V out. Now, your V out it is the voltage that you are measuring across the Zener diode. Your V out, it is the voltage that you are measuring across the Zener diode. Now, already we know what is the minimum voltage at V out, but now, what is the voltage across R? Then we're going to check at what current were we working with when we determine this output voltage here. You will see that our minimum current was what? Our minimum current was 0.25 milliamps. Then we're going to say your VR, which is the voltage across this component here. Remember, according to Kirchhoff, it says this voltage plus this voltage must give you that voltage there. This voltage plus that voltage must give you that voltage there. Then I will go and say, what is my VR? My VR, it will be my IZK, because that is at minimum point, multiplied by the resistance value that I find there plus your V out, which is your V out, which is your 11,813. Then with this parameter here, your VR, your VRS, your IZK multiplied by your resistor of the limiter there. What is your IZK? Your IZK is 0.25 milliamps multiplied by what is the voltage there? So what is the resistance there? 470 ohm. 470 ohm. Then within the calculator, then it's going to be 0.25 to the exponent minus 3 multiplied by 470. That is going to give you what? That is going to give you 0.1175. 0.1175. That is the voltage drop that I find within my component there. That is 0.1175. Now, then I will go and say, now when I substitute my V in at minimum will be given by 0.1175 plus 11,813. 11,813 plus 11,813, which gives you 11,930.5, which is 11,931 volts. So which means your voltage at a minimum, it must be 11,931, so that Zener diode can start regulate. So that Zener diode can start regulating. Then what will be the maximum voltage? What will be the maximum voltage? Andy, can you screenshot this?
Okay, one moment. You can continue.
Have you screenshot this?
Yes.
Okay. Then I will go and say at maximum, the first thing that I need to go and do, I will go and say, what is my IZ maximum? What is my IZ maximum? Now your IZ maximum will be determined by, the power dissipated across the Zener divided by your Zener voltage. The power dissipated by the Zener divided by your Zener voltage. Now, in this case, if you go back to your data sheet, you will see that the power ratings or the parameter of the power ratings of the Zener diode, it is given as 1 watt. The power rating of a Zener diode, it is given as 1 watt. If the Zener maximum current is not given, this is how you find the Zener maximum current. Now, with other data sheet, the Zener maximum current, it is given. But if it is not given, we can find the Zener maximum current. Now, in this case, your Zener maximum current is going to be 1 watt divided by your Zener voltage, which is 12 volts. Remember, we went with the typical Zener voltage. Now, in this case, we are going to say what will be the Zener current is going to be 1 divided by 12, and then in this case, it is going to be 83.33 milliamps. Are we getting the same value?
Yes.
Okay. Now, this is the maximum current that the Zener, this is the maximum current that the Zener can withhold. Then from there, then I will go and say, what will be my V out at maximum? What is going to be my V out at maximum? Now you'll say that your V out at maximum, it is going to be your V of Z plus your change in voltage, of Zener, your V plus your change in voltage of Zener, whereby your V of Z or your change of V of Z will be given by your I Z maximum minus your I Z T, or your current of Zener at test point, your current of Zener at test point, multiplied by the Zener impedance, Now, in this case, then you're going to say, what is your IZ max? Your IZ max is given by what? The change in Z. Your IZ max is given by 83.33 milliamps minus, what is your IZT? Your IZT, already we have determined there, it is 21 milliamps multiplied by 9. Then it is going to be 83.33 milli minus 21 milli multiplied by 9, which is 0.561. 0.561 volts. Now, with 0.561 volts, then your V out now will be given by the voltage of the Zener. What is the voltage? The voltage of the Zener, it is 12 plus 0.561. 12 plus 0.561, which means it's going to be 12.561. Now, this simply means that if I regulate with the maximum voltage, I'm going to regulate this Zener diode so that it can be at 12.561 volts. If I change my variable, to the maximum, I can regulate this voltage at 12.561. But
Sir,
what will be?
Sir,
Yes.
sir, can you please repeat V out? I don't hear it clear because the network here is talking.
Which one?
V out, I don't hear it. clear. I don't hear.
Oh,
Can
on
you
the
please
Vout.
repeat it? Yeah,
Where did you get lost?
starting from the V out.
From here.
Yeah,
Okay.
yeah, from there.
Remember, you want to regulate your output voltage to be stable at what? At 12 volts. Did you understand that part? But now, there is a certain voltage that you need to have within your input so that these 12 volts can be achieved. Did you understand that, that part? Now, for us to be able to see within which range must our input be so that you can regulate an output of 12 volts. Now, the previous calculation, for us to regulate at this Zener, or for this Zener to start regulate or to start giving us an output, it needs to have a minimum of 11,931 volts. Now, with the 11,931 volts, then we can start regulating our output at a V out that we determined previously. Did you understand that part? Then, when we want to find what is the maximum output voltage that this Zener diode can give out as a regulated voltage, then we're going to say V out at maximum. V out at maximum. What is the maximum current that can be dissipated? Also, what's the maximum current that can be withstand within the Zener diode? The maximum current will be given by the power dissipated, or the maximum power dissipated divided by the regulated voltage. The regulated voltage is the voltage that we find according to our data sheet, which is what? Which is 12 volts. Now, this current becomes the maximum current that this circuit can give out so that you can have an output of 12 volts, or a stable output of 12 volts. Then we're going to say what will be the output voltage at maximum current. The output voltage at maximum current, it will be the voltage. So the output voltage, it will be the voltage of the Zener, or the voltage at which we are looking for, plus the change in voltage. Now, with the change in voltage of Zener, because it is not a truly stable device, depending on the amount of current which is coming, then we're going to say it is going to be the current, or the maximum current given by the Zener minus the test current. Now, with the test current, simply means that at this current, then I will be able to give you 12 volts. At this current, I will be able to give you 12 volts. Now, if I subtract the two currents multiplied by the impedance that exists within this magnitude here, then I will be able to find what is my change in voltage. What will be the tolerance voltage that can exist? Then my V out will be given by the 12 volts that the Zener needs to give out, plus that small tolerance that exists because we are varying this input here so that we can get this voltage here. Then that will be your 12,561 volt. Now, with the 12,561 volt, this becomes the maximum voltage that can exist within the Zener diode. You will see that is 12,561, and then that one is 12, which means the magnitude, or the variant that exists, it is a variance of the magnitude of 0,561. Now, that 12 volt that I'm looking for, I can still use it at what? At 12,561, because that is the regulated voltage that I'm looking for. Did you understand that part?
Yes, yes, I understand. Thank you, sir.
Okay. Then, once we get these, then we're going to see our V in. Our V in, it is going to be a V in of what? Our V in, it is going to be a V in of what? It is going to be a V in of V R plus your V out. VR plus your VR. Now, what is VR? Now, in this case, you will see that your VR, it is a VR whereby now I look at what is the output or what is the maximum. Remember, at minimum, we had that. Now at maximum, we've got what? Sorry, we have got 83. Which means now here, it is going to be our IZ maximum multiplied by 470, then plus our V out, which is what? Our V out, which is 12,561. Then what is your IZ max? Your IZ max we've already determined as what? As 83, 83,33 to the exponent 3 minus multiplied by 470. Am I getting this correctly? No. 83,33 minus are we getting the same value?
I'm getting no,
Eh?
no,
Are we getting the same value? 39,1.
no, sir, we're not.
Eh?
I'm getting 51.726.
You're getting
51.726.
Masiwa,
Let's
can you,
recheck it.
sorry.
eh?
Masiwa, can you just move your camera a little bit? We can't see the bottom half of the board.
You
Just
can see
the
that?
last line. We can't see the last line on the board. Yes, yes, perfect. Yes, thank you.
Remember, this is your IZ max. What is your IZ max? Your IZ max is 83,33 million, right?
Yes, sir.
Then, if your IZ max, remember that is the maximum current. If your IZ max is 83,33 millions, then multiply
Yes.
by 470.
Yes.
It must be what? 39,
No, I added the 12.561
oh,
V
yes,
out.
yes, plus
Yes.
12,561 plus 12,561, which is
51.726.
51,726, which is 51,726 now, which is 51,726. Now, this output, also this input voltage, which means here you can regulate this up until 51,726. 726, 726 volt. Now, if I regulate to a maximum of 51,726, then I will get an output of what? I'll get an output of 12,516. I need to play within this magnitude, or I need to play within this range so that I can regulate my output to be at 12 volts. Now, this simply means that if I am not given the input voltage, I can be able to find the input voltage so that I can regulate my output to give me what is required according to Zener. Now, this type of a circuit, we call it a variable input regulator. Variable input regulator. Any question? No question. Okay. Now, then let's check. When we have a screenshot this only.
Okay, one moment. You can continue.
Okay. Now, apart from variable input regulator, we have what we call variable output load. Variable output load, so that it can give us a sustainable output voltage. So that it can give us a sustainable output voltage. Now, let's say, for an example, you are given an input a Zener diode with a variable output load, with a variable output load. Your RL, this is your RL limiter. This is your RL limiter, it's 270 ohm. It's 270 ohm. Now, then we say your input, it is your input of 24 volts. Your input is an input of 24 volts, which means here I will have current generated within this or energized here through the conducting wire. Now it needs to switch on this Zener diode. Now, when you switch on Zener diode, then the Zener diode is gonna regulate. But now, which Zener diode are we using? Then we go to the parameter of Zener diode. Then we go to the parameter of Zener diode. Then we say the Zener diode that we are using a Zener diode of this nature. It's a 1N4. Let's see. Yeah, it's a 1N4 734 7348. Yeah, it's a 1N4 7348, of which this Zener diode, the parameter of this Zener diode, it has a Zener voltage of, 5,6. Let me just mark it here so that I don't get lost. 5,6 volts. That is the output that this Zener diode can give out. That is the output that this Zener diode can give out. So which means when I measure on the output, I'm going to measure this voltage of the Zener diode during the reverse bias of this component, because it can only function when it is on a reverse bias mode. Then I will say, what will be my Zener test current? What would be my Zener test current? In this case, your Zener test current, your IZT is going to be 45 milliamps. It's going to be 45 milliamps, which means for me to be able to regulate this voltage, which means my Zener test current, it must be at 45 milliamps. It must be at 45 milliamps. Then from there, we go and check what is my Zener impedance. My Zener impedance at this nature, it is your VZ, it is 5 ohms. Your VZZ, it is 5 ohms. Now, remember, all of this information, you find it on a data sheet. All this information, you find it on a data sheet. Then your Zener knee current, let's see, your Zener knee current, in this case, it is going to be 1 milliamps. Your Zener knee current, IZK, your Zener knee current, it is going to be 1 milliamps. Your Zener knee current is going to be 1 milliamp. Then from there, then we can go and say, again, the information that we need, it can be an information of your IZM, which is your maximum Zener voltage. So your maximum Zener current, the maximum current that the Zener diode can withstand. Then that will be given by what is the power dissipated within the Zener and your Zener voltage. In this case, your power dissipated according to your data sheet, it is 1 watt divided by 5,6. 1 watt divided by 5,6. It's 1 divided by 5,6, which will give you 178, 571 milliamps. Did you get the same value as mine?
Yes.
Okay. Now this is the maximum current that the Zener diode can withstand. Then from there, then you will say, now let me start with my calculation. Every time when you, before you start with your calculation, first you need this information here. You need this information here because this information, it is the information that is being abstracted from your data sheet. That is your data sheet abstracted information. Then you're going to say at minimum. At minimum. Now, at minimum how? You need to find out what is the output voltage at minimum. What is the output voltage at minimum? Now you will see that for you to find the output voltage, I know that it can regulate 5,6 volts. It can regulate 5,6 volts. But at minimum, what would be the output voltage? At minimum, then you're going to say my V out at minimum will be given by your V of Z minus your change in V of Z. Your V of Z minus your change in V of Z. Where your V of Z, of change of V of Z, here you know that your voltage is 5,6 volts minus what is your change in voltage? Your change in voltage is what? It is your IZT minus your IZK multiplied by your ZZ. 5,6 minus what is your IZT? Your IZT test is what? It's 45 milliamps minus 1 milliamps multiplied by 5. Which means it's gonna be 5. That one is gonna be 44 milliamp because we do that one. Exponent 3 minus multiplied by 5. Then which is 5,38 volt. Did you get the same voltage as mine?
Yes, sir.
Eh?
Yes, sir.
Okay. Now, once you get these, then that is your V out at what? That is your V out at minimum. So now for this regulated voltage, so for this given voltage, when you regulate, when you start regulating, you're going to start regulating your Zener output voltage at 5,38, which means this is the minimum voltage that it can start regulating with. Now, once you get these, then you will say, what will be the voltage at maximum? What will be the voltage at maximum? Now, the voltage at maximum is going to be your V out is equals to your V of Z plus your change in V of Z. What will be your change in V of Z? In this case, it's going to be your 5,6 plus here is going to be your I Z max minus IZ max minus IZ T multiplied by IZ max minus IZ T multiplied by your V, sorry, your ZZ, which is your Z of Z. What is your IZM? You'll see that your IZM max, which is that one, your output, your maximum Zener current, which is 178,51. Continue this. Then here is going to be your 5, 5,6 plus 178,571 milliamps minus, what is your IZT? Your IZT, it is 45 milliamps multiplied by 5. Then your V out will be given by 6,268 volt. Is that what you get? Is that what you get?
Yes, sir.
Okay. Now that becomes your maximum output voltage. Now, once you find your maximum output voltage, then it goes and say, in a condition whereby this, it is not given. In a condition whereby this, it is not given, because this will give us what is the maximum current that is drawn from the supply. What is the maximum current which is drawn from the supply? Now, don't confuse the two. The maximum current that is the Zener diode, there's a maximum current of the Zener diode, and there's a maximum current that this supply can give out because you've got this component and that component there. But now, regardless of that statement, or regardless of how the maximum is, then you're going to say, if this one it is not given, if this it is not given, this can be determined But when you determine this, it is going to be your R of limiter. If it is not given, it is going to be R of the limiter will be given as your V in minus your V out at maximum. Do we understand each other? Your V in minus your V out at maximum. Remember, you've got V out at minimum and V out at maximum. So it must be your V out at maximum divided by your V out at maximum divided by your IZK. Your V out at maximum divided by your IZK. Now, that is when it is not given. That is when it is not given. But now, because it is given, which means we're going to use it as it is, then we're going to say, now we need to find what is the total current. Now we need to find what is the total current. Now, with the total current of the circuit, it is going to be an I total will be given by your V in minus your V out at minus your V out at minimum divide by minus your V out at minimum divide by your limit. Divide by R at limit. Now, Anli, can you screenshot this?
One moment. You can continue.
Okay. Then, you're going to say, now my IT will be given by, what is your V in? Your V in, it is 24 volt. What is your V out at minimum? What is the value that we find at V out at minimum?
5.38.
5.38 divided by 270 ohm. Which means it is going to be, sorry, it's going to be 24 minus 5.38 divided by 270. In this case, it is going to be 1, 2, 3. In this case, it's going to be 68.963 milliamps. I want you to verify it for me. Is it correct?
Yes.
Okay. Then from there, once you find the I total, which means that is the total current dissipated through the circuit, that is the total current drawn from the supply, then you're going to say, what is your I across the load? What is your current across the load. Now you see that your current across the load will be given by your I total minus your I ZK. Your I total minus your I ZK. Now with your I total minus your I ZK, what is your I total? It's 68,963 milliamps minus your IZK is what? It's 1 milliamps. 1 milliamps. Then you will say, I think here, if you do it correctly, it's gonna be 67,963 milliamps. Is this correct?
%, correct.
Yes, yes, correct. It's correct.
It is correct. Then,
This is correct.
once you find your IL, then you will then say, now I need to find what is my load resistor. But now, a load resistor, this load resistor, it is a constant load resistor so that it can give me an output of 5.6 volt. But now, this output or constant output resistor, it is a constant output resistor of RL minimum, of the minimum load resistor, so that you can have that voltage there. Then it's going to be your RL will be given by your V out or your I of air. Your V out of over your I of air. But now, V out when? V out at minimum. V out at minimum. Now, with your V out at minimum, what was your V out at minimum? It was 5.38 divided by, what is your L? Your L, it is 67,963 milliamps. What is the value there?
$79.161.
Wait. Let me just also verify 67,963. Which is 79,161. Oh, which means minimum, which is 79. Oh, then you can regulate your output to be at 5.6 volts. Now, those are the two conditions that you will find within the Zener diode, which means when we use Zener diode, we are using Zener diode to regulate the output. When you regulate the output, when you vary, you must know that I am varying so that I can find a constant output voltage. What is your input and what is your load resistor? Now, those are the two things that we need to work with when we work with a Zener diode. Now, the last part of the Zener diode, it is your Zener limiter. Now, with your Zener limiter, the same way we have done the diode limiter. Still remember with the diode limiter, the same way we have done this diode limiter, we also do the Zener limiter. If you go to your textbook, then you will see the Zener limiter and the diode limiter are more or less of the same category, or how the diode limiter is done. That is how the Zener limiter it is done. Now, this concludes our our chapter 3. Now, on chapter 3, on your own, I want you to look at the theory, and I want you also to look at the how do I put this? The other types of diodes. Now, with the other types of diodes, you just need to know what do they call those diodes and how do we use those diodes. What do they call those diodes? Their schematic symbol, and how do we use those diodes? Okay, thank you very much. Any question? If there is none, then you can enjoy the rest of your day. Ali, you can stop recording. You can still